Here's an example of using an integral to solve a problem of finding the area between two curves. Find the area of the region bounded by y equals sine x, y equals x minus pi, and the y-axis. The first thing we should do is get a simple graph of the region we're talking about. We have some coordinate axes. Let's get a very rough idea of the graph. For y equals sine x, we have more or less a sine curve. It looks something like this. We don't need to get it exactly perfect, but we need to get a rough idea of where it sits on the coordinate axes and how the other lines and curves that bound this region relate to it. So we know that the graph of y equals sine x passes through the origin right here. We also know that it's going to cross the x-axis again at pi. Let's mark pi right here, just where it's convenient. And we know that our curve is going to go up and back down again at pi. It's going to continue to go down and back up. And if we need to draw more periods of this graph, then we can do that later. We'll also extend it in the negative direction along like this. This is a good enough idea of what our graph looks like. Now, in a different color, let's draw the graph of y equals x minus pi. That's very simple. That's just a line that crosses the y-axis at negative pi, and therefore it's going to cross the x-axis at pi, so it's just a line that looks like this. Here's y equals x minus pi. The last line that bounds the region is just the y-axis, right here. So now we know what our region looks like. Here's the region that we're interested in finding the area of. How should we set up our integral to solve this problem? Well, thinking back to our problem of doing a Riemann sum and how that relates to integrals in the previous example, it might be helpful for us to draw a typical Riemann rectangle here. If you're going to slice up your region into thin rectangles that you can find the area of easily and use that to approximate your region, one of those rectangles might be, let's say, this one right here. Here's a very thin rectangle, one of many that we could slice our region into. Let's say it's at position x. What is the height of that rectangle? That's actually pretty easy. It's going to be the top function minus the bottom function. In other words, the top y value minus the bottom y value that correspond to that x. That's going to be sine of x minus x minus pi. Now, be very careful here. I don't mean sine x minus pi. I mean sine x minus the entire expression x minus pi, which means I need to put it in parentheses. Watch out for that. In lots of integral problems that we solve, you'll find that you need to make clever use of your parentheses to ensure that you are adding and subtracting the correct things. Always watch out for that. Anyway, that's the height of our rectangle. In fact, that's going to be the height of every rectangle that we could slice our region into. The only thing that will change is the value of x. What's the width of our rectangle? Well, that's right here on our graph. It's this distance, the horizontal width of that rectangle. That's going to be the change in x as you move from this rectangle to the next one. We could call that delta x if your rectangle has some non-infinitesimal thickness, but because we're planning on doing integral, let's straight away turn that into dx. Our width of our rectangle is dx. dx is an infinitesimally thin change in x. Great. What's the area of our rectangle? Just multiply these things together. It's going to be sine of x minus pi, don't forget those parentheses, all of that times dx. Great. Now we just need to add up this value for every one of the rectangles that we would use to approximate the area. And if we want to get the exact value, then instead of doing a sum, we'll compute an integral. Now we're ready to solve our integral. We've more or less set it up already. We need the integral of sine of x minus pi, don't forget those parentheses, times dx. We just need to know what are the bounds on x. That's pretty easy to figure out. To find the bounds on x, we just consider what is the leftmost x value that we care about, which is right here at 0. And what happens if we let our x range all the way up to the rightmost x value we care about, which is right here at pi. Our bounds, therefore, are 0 and pi. Now we're ready to go. The first thing we should do in solving any integral is simplify it as much as we possibly can. Those parentheses that we put in around the x minus pi were useful because they're going to ensure that we add and subtract the right things. But they're also getting in our way. Let's just rewrite this right away. In fact, we can just rewrite this integral right now. This equals the integral from 0 to pi of sine x minus x plus pi dx, of course. This is a pretty easy integral to solve. We'll just find the antiderivative of each term. So the antiderivative of sine x is negative cosine x minus the antiderivative of x, which is x squared over 2, and plus the antiderivative of pi. Of course, the antiderivative of a constant is going to be that constant, pi, times x. This is evaluated at 0 and pi. So we'll just need to plug in our bounds. And watch out, by the way, you might be tempted to see that bound of 0 as the lower bound and think that when you plug it in, you'll just get 0, but that is not true in this case. Let's plug in our upper bound first. We have negative cosine of pi minus pi squared over 2 plus pi times pi. Now we're going to plug in our lower bound. We have minus, let's put some brackets this time, minus negative cosine of 0. As always, I've run out of room. That's okay. That's always going to happen pretty much. Minus 0 squared over 2 and plus pi times 0. And we'll just do some computations and work that out. This is something you can and should do without a calculator. You should be familiar enough and comfortable enough with trig functions of basic angles like pi, pi over 2, pi over 4, those kinds of things, that you can compute the cosine of those things without a calculator easily and comfortably. It's not that calculators are bad, it's that it shows that you understand your trig functions well enough to be able to handle this. Okay, this equals, well, the cosine of pi is negative 1, so negative cosine of pi is negative 1. Okay, minus pi squared over 2 plus pi squared minus, all right, lots of negative signs here. Better watch out. I'm going to keep my parentheses for now here, my brackets here. Negative cosine of 0. Cosine of 0 is 1, so there's a negative 1 there. minus 0 plus 0. So I'll just say minus 0 plus 0 just for completeness sake. Close that bracket. And now we are pretty much ready to go. What have we got here? Well, we've got a negative, negative 1. That's a plus 1. And we've also got negative, negative 1 over here. That's another plus 1. So really we have 2 minus pi squared over 2 plus pi squared. That's just plus pi squared over 2. So here's our answer. 2 plus pi squared over 2. That's the area between the curve y equals sine x and y equals x minus pi and the y-axis.